Good morning, everyone. I'm Zeng Lingyu. Today, I'd like to introduce my paper, Detecting Rumor on Microblogging Platforms via a Hybrid Stance Attention Mechanism. My presentation consists of 5 parts, and I'm going to start it with the introduction section. With the rapid development of the Internet, the microblogging platforms have become important social medium as well as ideal platforms for rumor spreading. Once rumors on microblogging platforms are out of control, sphere of influence would be extraordinarily large. For example, after the college entrance examination, a rumor that the daughter of a person who is in debate cannot be admitted to university has become popular on Signal Weibo. One of the tweets is read more than 30,000 times. However, the efficiency and speed of the rumor refuting are insufficient. As shown in the picture, only 67% of rumors are reported to Weibo platform in the first 24 hours, and Weibo platform needs to average 17.6 hours to verify them. To cope with these problems, automatic rumor detection methods are required. To detect a rumor automatically, first, we define the problem. We formulate a retweet and relevant retweets as a microblogging event. The overarching theme of our research is to identify whether the retweet is a rumor based on the data of the whole microblogging event. This slide shows the example of microblogging event, which contains 1 retweet and 5 retweets. According to some researchers, user stances are an important feature for rumor detection. But stance information released by different users has different importance for rumor detection. As shown in this slide, retweet 1 is the text generated by default when the user forwards a microblogging but doesn't comment on it. Retweet 2 is a supporting tweet, with just a repetition of retweet. Retweet 3, retweet 4, and retweet 5 convey querying and denying stance respectively. Among all these retweets, retweet 3, 4, and 5 are the texts containing more valuable information, and that is the information we need to pay more attention to. In this paper, we test the hypothesis that more valuable stance information for rumor detection can be extracted by paying different attention to different threat-level stance information. Our contributions can be summarized as follows. First, to the best of our knowledge, we are the first to use the attention mechanism in an event-level stance representation learning process. The latent representation obtained in this way contains more valuable and reliable information for rumor detection. Second, the hybrid attention mechanism is consisted of content attention mechanism and user attention mechanism, evaluating the importance of stance information from the aspects of text contents and user's credibility respectively. The hybrid attention mechanism enabled the model to contain more important information in the latent representation of the event-level stance. Third, experiments on a real-world dataset from Weibo platform demonstrate that our proposed model improves the performance of rumor detection in terms of both efficiency and accuracy compared with other methods. After the introduction, I'm going to introduce the related work. First type of automatic rumor detection model is based on feature sets. For example, some researchers use supervised machine learning methods for rumor detection by constructing feature sets. The shortcoming of them is the requirement of daunting manual effort. Second type of automatic rumor detection model is based on deep learning. Some researchers exploit a recurrent neural network or convolutional neural network for rumor detection. The shortcoming of them is the neglect of stance information. Of course, some methods also take the stance information into consideration. The main drawback of these methods is that they treat all the stance information equally. To overcome the drawbacks mentioned above, a model which can use stance information effectively is required. We propose a model with a hybrid stance attention mechanism to make full use of the user's stance information. Our model consists of 4 modules: stance module, attention module, rumor module, and integrate module. In our model, first, tweet-level stance representations are learned in stance module. Second, hybrid attention mechanism is leveraged to construct event-level stance representation. Third, the rumor module captures the content feature and temporal features of a microblogging event and constructs a latent representation containing the information directly related to rumor. Finally, the integrate module combines the rumor representation with the event-level stats representation and the input of the ultimate rumor detection classifier. In stance module, we constructed two different structures to capture stance features. As shown in this slide, some stances are expressed by colloquial expressions like in tweet 3 and tweet 4. Really, and it's fake, a colloquial expression for query and denying stances regardless of rooted. We defined this type of feature as a grammatical feature and we construct a convolutional neural network to extract these features because of the advantage of the convolutional neural network in local feature extraction. The convolutional neural network is shown as the picture on the right side of the slide. Apart from grammatical feature, there is another type of feature related to rumor detection. Retweet 5 says that the boy in the picture is her neighbor, and he has grown up, which means the boy could not have been lost for 2 days. Although it's a post that suggests a denying stance, it's impossible for a model to tell the stance unless the model knows the content of the rooted. To deal with the problem above mentioned, we construct a recurrent neural network to capture the event-level stance feature. In the event-related feature extraction structure, first, a recurrent neural network using the GRU cell is constructed to encode the rooted, and then the output of the rooted layer is used at the initial state of the retweet layer. In this way, the information of rooted is taken into consideration during retweet feature extracting. After tweet-level stance feature extraction, a hybrid attention mechanism is used by our model to identify and integrate important information during the event stance representation generating process. Two different attention mechanisms are used in the attention module. Content attention mechanism uses the output of the stance module to evaluate that how much important information a text contains, and user attention mechanism evaluates that how reliable the user stance is. The network structure of the attention mechanism used in our model is shown on the picture on the right side. The ith input of the content attention mechanism is the stance vector of the ith tweet, and the ith input of the user attention mechanism is the vector of the ith user. For each attention mechanism, we calculate the element-wise multiplication of the attention scores and the inputs. Then, we sum up all the vectors along the column and get two vectors from the two attention mechanisms. Finally, we calculate the mean value of the two vectors and the representation of the event-level stance is obtained. In rumor module, to extract temporal and content information efficiently, we construct a recurrent neural network to extract rumor-related features. Microblogging events comprise a sequence of correlative microblogging posts. It's inappropriate to input a post once a time, which requires the recurrent neural network if consisted of thousands of layers. Hence, in rumor module, we first split a microblogging event into n sub-events. We treat a sub-event as a document and use the TF-IDF value of the vocabulary terms as input. Since the TF-IDF value of the vocabulary terms constructs a sparse representation, we also implement an embedding layer to convert the sparse representation into low-dimensional representation. In integrate module, the outputs of the attention module and rumor module are concatenated together and put into the classifier. The next section is experiment. There are two datasets used in the experiments. The first one is Weibo stats dataset, and the second one is Weibo rumor dataset. Both of them are public datasets, and the basic information of them is shown in table. As demonstrated in the following table and figure, our model outperforms these state-of-art methods. These three models are our model and its varieties. Simple RNN is a model that only contains the rumor module. The output of the rumor model is put into a full connection layer and a softmax layer to detect rumor. RDM-SN is a module without attention module. RDM-HSAN module is a module containing stance module, attention module, rumor module, and integrate module. The simple RNN model achieves 0.89 for accuracy on the dataset, indicating that the basic RNN can learn discriminative features effectively. RDM-SN model with a better performance than the simple RNN model validates the enhancement effect of the event stance information. Compared with RDM-SN, which doesn't use attention mechanism in event stance representation constructing process, the model with attention mechanism, that is RDM-HSAN model, achieves better performance, indicating the effectiveness of attention mechanism. It demonstrates that more contributive information is contained in the event stance latent representation when the model leverages an attention mechanism. We also compared our model with baselines early rumor detection experiments. Given a detection deadline, early rumor detection is a detection using the twist published before the time point. In early rumor detection experiment, our model has a better performance after 24 hours. That is explainable because it takes a while for users to browse rumors and express their stances. Compared with the time lag caused by the authorities' rumor verification, 24 hours is an acceptable time lag. The next section is conclusion. To make a brief conclusion, in this paper, we propose a rumor detection model with a hybrid stance attention mechanism, which performs well in both rumor detection and early detection experiments. In future work, we can also develop an unsupervised model to cope with the massive unlabeled stance data. Thanks for listening.